So here we will be focusing on how to leverage the FPGA reconfigurability, for hardware obfuscation. So to give a little bit of introduction and a little bit of recap, we know that today the IC design, market, or the vendors, they actually outsource fabrication from third-party foundries. It means that they do not have a capability in-house to fabricate their ICs their own, right? So the fact is, as I explained earlier in the previous lecture, that this requires $1 billion, right, to build the fabrication facilities such as Taiwan, semiconductor manufacturing company, or Intel, or Samsung. These are all advanced technology, right? So that's why there is a thing that we call globalized IC supply chain. Means that the whole IC supply chain from from design, fabrication, testing, blah blah blah. These all stages. These are actually spread over the globe, right? Over the globe, and that's why we have some kind of threats, right? For example, reverse engineering over production, hardware trojan, and piracy, etc. So previously we studied a technique that we call logic locking. We lock, logic behind a secret key, right? Or we try to hide a logic or obfuscate a logic, right? So now let's do a little bit of, recap or the history that the reconfigurable logic evolved over time, right? So we have a first, field programmer grade array logic, and it was a device that was actually invented by Xilinx in 1984. And then, this architecture, it become a, need for the industry, and then they increase the capacity and VRAM. And then after that, in early 2000, there was a, new thing called embedded FPGA. They try to embed FPGA inside the SoCs, and they introduced the flash-based FPGAs, and then this whole process, it actually evolved so rapid that today we have a very good FPGA architecture in FinFET technology, right? Most of you guys know MOSFET technology, and then we have a FinFET technology, right? So if someone wants to study more, he or she can just type of FinFET, and then you can learn a lot of knowledge on Google. So, and then this happened, and this is, we can see that today we have kind of specialized architecture, that are FPGA that can even run, machine learning algorithm. So that is the history of reconfigurable logic. So the application in the security. So previously we saw this slide also. So I would like to recap that we have here eFPGA, which is embedded inside the ASIC, and then we have logic locking. We have a fine grain, and we have coarse grain, logic. So fine grain is the logic locking, and coarse grain is the eFPGA. And both of them, they serve to lock the logic behind the secret key. And if we move from left to right, we can see that there is a increase in the security and increase in the PPA, power performance area overheads, right? So the fact is that we, have one type of the reconfigurable lobby, and there are many other types. We can also use the reconfigurable in different ways and on different levels. Let's try to see how many types, how we can classify the reconfigurable-based obfuscation. So we can classify the reconfigurable-based obfuscation, or REbo for short, on the base of technology, right? We have a technology. We have SRAM, where we store our logic, SRAM LUTs, right? SRAM means where we store our bit stream, and there is a LUT that is that makes our combination logic. And then we have non-volatile based memory, right? These are also, for example, if we go in detail, there are, for example, spin orbit, technology, right? Spin orbit. And then we can also have, like, other approaches like MRAM LUT, for example, magnetic memory based logic. So there are different types of technologies to store the bit stream of the um, logic, right? And then we have different elements, right? We can only leverage lookup tables, right? We can leverage switch boxes, right? That we can configure switch boxes so that we can, route, make some reconfigurability feature, or we can use both LUTs and switch boxes, right? On the other hand, we have IP type, right? We can use soft IP. Soft IP is like we just get RTL, right? And then we do our whole, logic synthesis and physical synthesis. And then we get firm IP. We have a netlist, right? And then we have hard IP. It is kind of, layout. We have, left files. We have what we can say liberty files, and then we, just directly integrate in the physical synthesis. So these are all different types of the reconfigurable with obfuscation, that we can leverage. So let's summarize this global picture here. On the right hand side, we have a traditional FPGA that is fully reconfigurable. It is flexible. We can map any logic on this device, right? All right, sorry. On the left, we have ASIC, which is actually a static, and it is rigid. We cannot change the logic after the fabrication. For example, the chip used in our mobile, we can't do anything, right? And then we have two different things in the middle of this, right? We have eFPGA, we have a hybrid ASIC that we studied, right? So just to recap, I mean, we are using here only the lookup tables, right? So if we classify this one, this is kind of LUT-based obfuscation also. And then the goal was that we try to provide a flexible platform where the designer can meet security and PPA trade-offs, right? We don't want the strict security, neither the strict security nor the strange, the logic. For example, ASIC, there are better approaches. Else, the middle of these two, extreme words, it can be a kind of midpoint solution, which we term, hybrid ASIC. So that is the goal. And the designer has a lot of choice that we will see later how the designer can do these all things, right? And controllability over this design versus security trade-off. So this is the tool that I built many years ago for this purpose. So here we can see that it has three different ways. First, we synthesize the design on traditional FPGA synthesis tools, for example, Vivado. We give the RDL, we give the timing constraint, and then we synthesize. On the output of the synthesis, we get the timing report from FPGA. So this is kind of the thing that we have a baseline structure, baseline architecture, right? And we have FPGA. We get synthesized netlist, and then we start our obfuscation phase, where we have a standard cells library of, for example, 65 nanometer, TSMC. And then we have a parser which reads the netlist, and then it actually reads all the primitives, FPGA primitives. If you know the FPGA architecture, we have CLBs. In the CLB, we have a carry block, we have lookup table, we have flip flop, we have mux. So, and then these all primitives, they combine and make a configurable logic block we call CLB, right? So we try to identify that one, and then we try to identify the critical path. If everyone can understand, the critical path is the worst path in the design. I mean, but slowest path, in the design, right? And then we try to ignite our obfuscation engine. What we did today, we provide a user, provided obfuscation criteria. It means that we try to start from the extreme case that we have PGSL, and then we start replacing, from the critical path that with the ASIC cell, ASIC cell, which is actually standard cell, and the FPGA cell is the lookup table, right, which is the slowest cell. And then we, in a layman terminology, we keep on, repeating this process until enough number of the LUTs have been converted to the ASIC cell. And then we also interface with the timing engine so that we can keep track of our TNS and WNS, means worst negative slack and total negative slack, so that we can also evaluate the performance over the obfuscation phase, right? And then we export the hybrid design, which is a mix of standard cells and reconfigurable cells like lookup tables. And then we can actually execute our synthesis, normal logic synthesis, and then place on doubt, and then we do the tape out and send to the foundry. Once the design will come, we will feed the build stream and we will recover the reconfigurability, the functionality. So this is the whole flow of the tool, right? That is fully automated, and we have full control over the and this is actually done on the pre-logic synthesis phase, right? So the fact is that we don't want to waste a lot of time, and we want to do the preliminary design versus security analysis, right? Because RDL to GTS is a full time consuming flow, right? Especially the physical synthesis place and route, and then things become more, static there. So we don't want to waste time. So we try to, provide this platform in the early phase. So here are some of the experimental results. I mean, these results are from the physical synthesis, and they are actually very close to the silicon, right? So it means that if we have look in the first row, we have 100%. It means that we have hybrid ASIC, which is actually fully reconfigurable, analogous to FPGA, right? And then we have its area, frequency, and dynamic power. And we also synthesize this design on, FPGA. So, and this runs on 77 megahertz. So, I mean, we can compare. So, if we compare the FPGA versus our fully reconfigured design, so we can say that our design runs faster, right? So we start decreasing the obfuscation level, right, from top to the bottom. We start decreasing the obfuscation level. I mean, the percentage of design that we are trying to hide, we start decreasing it, and then we try to see the trend, so that we can see that the area is decreasing, frequency is actually increasing, right? And then we also have the similar trend for dynamic power, right? We have a decrease in the dynamic power, right? And we can also see the design density. It almost remains 80%, right? So to be honest, to be very honest, we don't have a quality of result. This is a good result, but we are, greedy, and we want to actually optimize it, right? So that's why I come up with another technique. Like in my design, actually, we will see in the layout later. We have, lookup, 2 input to 6 input lookup table. That is actually standard for, Xilinx flavor FPGA, right? If you go into the Intel, they have even the 8 input lookup table, right? So we have maximum 6 input lookup table, and if we see in this example, it's 6 input lookup table. We try to implement 6 input AND gate, right? And then what we did a kind of decomposition, or we can say Boolean factorization, right? Um, in that case, we try to decompose the bigger LUTs into the smaller one lookup table, and then we try to implement the same functionality, but the smaller LUTs, so that we can get smaller area, right, and power, and also more fine grain elements. So the number of the reconfigurable elements will also increase, and it will be more fine grain. We have to see from the reverse engineering point of view also. So if by having this small example, we decrease the depth, right? We decrease the area, we decrease the delay, and also the number of registers to store the bit stream, right? So in every LUT, we actually have some flip-flops. We don't use the RAMs or VRAMs to store the, so it is all inside the lookup table, right? So, okay, so if we see our, the layout here, right? So we can see here placed, right? The placed layout here. On the left side, we can see the, the placement of the lookup tables and placement of the standard cell, right? So we can see that we have most of the 6 input lookup table, right? We can see some kind of yellow stuff, right? And then we have empty spaces that are actually filled by standard cells. And then on the left two panels, right, and the right panel, we have the routed layout. And we can see the density. Density means, the routing density. So we can see that how dense is the design. I think we have this, if you see the pink and this kind of orange metal, this is actually M6 and M7. So we have a lot of density for M6 actually. So similar design, right, with 80% obfuscation. If you see the right two panels, right, in the slide, I don't know, I cannot use this. Oh, I can use actually the laser pointer. Sorry. Um, Here, right? So in this layout, we can see that we have this decomposed variant. Now we can see that here we can see the area. We can see the the it almost decreased by kind of 50% or 45%. And then we can see that we have a lot of two input or three input LUTs, right? And we can see that we have if we I try to zoom here, right? Uh, it's blurry. We have very tiny spaces as compared to this layout, right? We have large spaces between the LUTs. We can see them. You can see a lot of the red stuff here, right? And here you can see very tiny spaces, right? And we have very few, if you see the orange stuff, 6 input lookup tables. And then if you see here the routing, so we can say that after decomposition, we have a very relaxed design, almost relaxed as compared to this one. And I think M7 is barely used there, right, for the routing. So let's compare the robustness here. We can see that we have 80% this design, which we call baseline design, and then we have the optimized design, right, which is a decomposed variant. So we can see that here, you see the density is decreased. Area is also decreased here. And we have a 40% gain in the frequency, right? And also the decrease in the dynamic power, right? So we can see that we get some optimization from this decomposition. And this layout, the routed, it's tape out ready layout, and we can send and fabricate. Let's do the little bit more analysis. Previously, we have so we have the here now 85% variant, right? We increase a little bit of the we can say the obfuscation level, right? And we try to see that how does the placement of the lookup table happens in the design. So we see we have a similar kind of trend. We can see a kind of regular tiles that are placed. This is very good sign because if we try to reverse engineer and we try to there is one thing called assemble, right? Assemble design in physical, since I don't know if you know it. If you try to assemble these macros, and after the assembly we will see everything will be in the standard cell. So from reverse engineering point of view, everything will look like a regular structure. I mean, if the foundry or attacker, he or she wants to do the reverse engineering the layout, he or she has a very hard time to quantify the LUTs, right? First of all, if we try to build a threat model, which is given in the paper, he or she has to identify the type of the LUT. He or she has to identify the connectivity, how the LUTs are connected, and then structure of the LUTs, and then there will be a point where he or she will try to get the guess of the bit stream. So that's from the security point, security analysis of this, we can say. And then if we see the magnified view here, so we can see, I mean, kind of very regular placement of the lookup tables. So let's go to security analysis. Once we have this obfuscated design, right, we need to perform some security analysis, and to say that we can ensure that design is secure against the state-of-the-art attacks, right? So as we studied in the last lecture, we have two different type of the attacks. One is the oracle guided, and one is the oracle less, right? And then we perform both of the attacks. There are many attacks which are Oracle-less also. So we here perform one of them which actually exploit the structural analysis, the structure of the design and the resynthesis. So here in this in these two panels, we can see on the left side we have right Oracle guided attack, which is actually SAT attack, and we actually execute three different flavors of the SAT attack. One is the traditional SAT attack, one is the app SAT, right, and one is the ADPG guided SAT attack, right. So let's see what happens. On the x-axis, we have this obfuscation level, which is the if we increase the obfuscation level, number of the reconfigurable elements will increase, right? So if we increase the obfuscation level, we can see that the execution time of the SAD is actually increasing, or we can say that. So here, this is the green line on the 40% of obfuscation level. At that time, this SAD attack actually saturates the straight line. We call it timeout. It means that SAD attack is timeout. It cannot find the solution of the circuit. It cannot break the circuit, right? So this is the case for all these three SAD attacks. Let's try to see the execution time. Execution time is kind of a metric which we use in a simple way, and we try to see that after it's this kind of exponential behavior until 40%, we can say, and then it actually saturates, and similar to the you know what we can say, the other design. So this is the C552, right? And here we have the C552 optimized variant. So we can see that after the optimization, what actually happens, we reduce the number of LUTs, the bigger LUTs, increase the number of the LUTs, but we decrease the bit stream size, right? But still we hold the similar security level, right? So that is the fact. Okay, now if we move to the Oracle-less attack, which is the here is scope, here I give a reference. This attack actually, if you give you short intro, it is kind of a resynthesis. We take the design, we resynthesize, we find a very small part of the key, we give to the key to the lock design, we set the this lock design as a constant values, resynthesize again, get a new structure, resynthesize over and over in time, and we try to guess the key, right? So that's why I told many times the structural analysis is so powerful, right? It is base of many attacks in the hardware security. So we can see that with the increase in the obfuscation level, the execution time is kind of linear, if we have, right? And then we can see that there is a COPE metric. The COPE metric is the vulnerability metric. Vulnerability means that how much design is vulnerable. So if we see in this figure, right, we can see that the trend for both baseline optimized design, the vulnerability metric is actually decreasing. It means that increasing the obfuscation level decrease the vulnerability of the design, right? So this is the Oracle and Oracle guideline. There are other attacks also that are given in the paper. You can, read and try to understand. In general, if I conclude that we have a hybrid ASIC which actually contrasts with the eFPGA redaction. eFPGA redaction, we have tiny eFPGA block, we can say, which is a kind of redacted when we try to place the small but most sensitive part of the design, right? So here I developed a custom tool. In my case, we have design versus security trade-off on synthesis level, and then we have experimental results. We have physical synthesis, which actually confirm that we have met the goal of the flexibility of the midpoint solution, that is hybrid ASIC, right? And then we have Oracle guided and Oracle-less attack that actually confirm the security hardness, And then we have compositional structure attacks, and they actually suggest that we should obfuscate the design on a very high rate, right? The more details are given in the paper. If someone wants to read more, he or she can go and read the paper and ask the question, and I'm happy to answer question here or even after on the email.